Hi, this video is going to be about integrating trigonometric functions, and it should follow the pattern of the other ones that we've been looking at under integration. So we'll start off by just recapping what we did with differentiating trig functions. So if we take a look at the derivative of sine of ax plus b, remember this is a compound function, so we're going to have to differentiate that part over there first of all, and then differentiate the whole thing. So if I go and find the derivative of ax plus b, well, that's going to be a by itself, and then the derivative of sine is going to be cos, and it's going to be the cos of ax plus b. So there we have the derivative of sine of ax plus b. The next one, when we go to cos, again we're going to need to look at the derivative of ax plus b. That's once again simply going to be a. Derivative of cos is going to be minus sine of that function ax plus b. So in other words, it's going to be minus a sine of ax plus b. And then finally, when we come to look at the derivative of tan ax plus b, well, obviously the derivative of ax plus b is going to be a, and then the derivative of tan is going to be sec squared ax plus b. So there we've got the derivatives of each of those functions. So now, if we come and take a look at the integral of these different functions, the integral of sine ax plus b, we've got to ask ourselves the question, what did I derive in order to get sine? So here is the sine part over there, ax plus b. What did I derive to get to that stage? I derived cos. So I'm expecting to see that I'm going to have cos ax plus b. But if I go and derive cos, I'm going to get a minus sign. I don't have a minus sign over here, I have a positive sign. So this thing would have had to be negative to start off with. Also, if I go and derive minus cos of ax plus b, I'm going to end up with sine ax plus b, and I don't have an a in front of there, so I'm going to have to put all of this over a. And then obviously I have to add the c on afterwards. Likewise, if I go and look at the integral of cos ax plus b, what did I derive to get cos? Well, I derived sine to get cos. So in other words, I'm looking over here at sine of ax plus b. I don't have to worry about a negative because the derivative of sine is positive cos, and I've got a positive cos here. But I do need to take into account the fact that I've got an a inside that bracket, so I'm going to have to divide everything by a and then add on c. And finally, what did I derive to get sec squared? Well, I derived tan to get sec squared. But again, I had to divide it all by a in order to get the right coefficient. And obviously at the end, I must add on c. So here we have the integrals of those three functions. Those formulas are on the formula sheet, so you just need to think about how we went about getting them every time you use them. So let's have a look at this example, some examples now. The integral of the sine of 3x dx. Well, what did I derive to get sine? I derived minus cos of 3x. But if I derived minus cos of 3x, I'd have got 3 sine of 3x, so I must divide all of this by 3. And then I'm going to add on c. What did I derive to get 3 cos 4x? Well, maybe just to make it a little bit easier for myself, I'm going to take that 3 out, and say, what is the integral of cos 4x dx? What did I derive to get cos of 4x? Well, I've got my 3 in front of that. I'm going to put my bracket here. I derived sine to get cos, so I'm going to have the sine of 4x, but I must divide all of that by 4, and then I must add c. So in fact, this is going to work out as being 3/4 sine of 4x plus c. Moving on, I've got the integral of 4 sine x cos x. Now we need to think about this sine x cos x. Hopefully that rings a bell to you. Hopefully you can see that I could rewrite this as 2 times 2 sine x cos x dx. In other words, I could go and pull that 2 and put it in front of the integral sign. And hopefully you'll be able to tell me that the 2 sine x cos x could be written as the sine of 2x dx. Now I've got myself back to, the example, something similar to the one that I started out with up there. So what am I going to have here now? I'm going to have 2 times, what did I derive to get sine? Well, I derived minus cos. The angle was 2x, but because it is 2x, I must go and divide all of this by 2 in order to take care of the coefficient, and then I must add c. So if we tidy that up, let's just give it a little bit more space underneath it. If we tidy that up, that 2 in the front and the 2 down the bottom will cancel out, and I'm going to be left with minus cos of 2x plus c. There's my integral. Now, quite often you're going to come across integrals that involve sine squareds and cos squareds. And once again, you're going to need to think back to the work that you did on double angles and the identities that we got out of double angles. I'm just going to recap those briefly, especially the double angles that gave us squared ratios. So if you remember, the cos of 2x could be written as cos squared x minus sine squared x. And that meant we could rewrite this as in 2 ways, either as 2 cos squared x minus 1, or we could have written it as 1 minus 2 sine squared x. And that means we can rearrange this in 2 different ways. I'm going to need to give myself a bit more space here. So I've got that cos 2x is equal to 2 cos squared x minus 1. And if I rearrange that, I can get cos 2x plus 1, all of that divided by 2, and that's going to give me cos squared x. Or if I take a look at it with the other option that I had over here, I've got that cos 2x is equal to 1 minus sine squared x, and so 2 sine squared x, sorry. So 2 sine squared x is going to be 1 minus cos of 2x, and so sine squared x can be rewritten as 1 minus cos 2x all over 2. So when I come up with the integral of sine squared x dx, I'm going to have to work with this part over here. Now, I've got a fraction there, all over 2. So I can go and rewrite this as the integral of a half 1 minus cos 2x dx. I'm going to take that half out the front just to make things easy to work with. So I'm now going to look at the integral of 1 minus cos 2x dx. And so that's going to give me a half. What did I integrate to get 1? Well, I integrated x to get 1. What did I integrate to get minus cos? Well, that would have had to be minus sine 2x, and that would have all had to be over 2. And then that's going to have a c added on the end. So now when I come to look at the integral of cos squared x dx, I need to go back and take a look at my cos squared x. There was the formula written up over there. Cos 2x plus 1 all over 2. So in other words, I can rewrite this as the integral of a half of cos 2x plus 1 dx. I take out a half, I have the integral of cos 2x plus 1 dx. And now I just have to integrate each of those, and this is going to give me a half. What did I derive to get cos 2x? I derived sine in order to get cos, so this is going to be sine of 2x all over 2. What did I derive to get 1? I derived x to get 1, and I have to add on a c at the end. And so here I have the derivative of cos squared x. The final example that we're going to look at is an example that deals with exact values. And as Cambridge likes to do, here we have a question that involves 2 different skill sets, working with the special angles and also working with integration. Now we're working with the angle pi over 3. Pi over 3 is the same as 60 degrees, but you mustn't let them know that you're thinking in terms of degrees. So we need to draw our special triangle. Here we have pi over 3. I know that's 2, that's 1, and that's going to be root 3. So there I've got my values that I'm going to work with. I now need to look at integrating this thing. So what am I going to have here? I'm going to have the integral between 0 and pi over 3. No, I'm finding the integral, so I don't have to worry about that. What did I derive to get sine 2x? Well, I must have derived cos 2x. In fact, I must have derived minus cos 2x. And all of that's going to be over 2 in order to deal with the coefficient. And then I've got to figure out what did I derive to get cos 4x. That must have been sine 4x, but I've got to make sure that I divide that by 4. And that I'm going to consider between 0 and pi over 3. So what have I got here? I've got minus a half cos 2x minus a quarter sine 4x. And that's going to be between 0 and pi over 3. Now my reason for doing this is that I want to take out the fraction minus a quarter so that I can work without having to deal with fractions. That means I'm going to have 2 cos 2x plus sine of 4x, and that's going to be between 0 and pi over 3. So now I just have to substitute in, and what am I going to have? Well, first of all, I'm going to have 2 cos of 2 pi over 3 plus the sine of 4 pi over 3 And from that, I've got to take away 2 cos of 0 plus the sine of 0. And I need to include those last two because the cos of 0 is 1. I mustn't forget that. Okay, carrying on here, I've got minus a quarter. And I'm talking about the cos of 2 pi over 3. The 2 pi over 3 is in the second quadrant. And that's going to be the same as minus the cos of pi over 3. The cos of pi over 3 is 1 over 2. So this is going to be 2 times minus a half. Sine of 4 pi over 3. 4 pi over 3 is in the third quadrant. Sine is negative in the third quadrant. The sine of pi over 3 is root 3 over 2. So this is going to be minus root 3 over 2. So that's the first part done. And then I've got to take away 2 times the cos of 0, which is 1. And the sine of 0, which is 0, so I can forget about that. Okay, tidying all of this up. What have I got here? I have got 2 times a half minus a half, which is minus 1, minus root 3 over 2, minus 2. And that means I've got minus a quarter times minus 3 minus root 3 over 2. And that means I'm going to have 3/4 plus root 3 over 8. And there is my exact answer to that integral. Right, hope that helps. Now you need to go and practice. Thank you very much. Goodbye.